My name is Justin Moore. I'm going to talk to you guys about virtual CPE solutions today for service providers. A little bit about myself. I work for PLUMgrid. I'm a principal solutions architect. My background is leading complex technology initiatives within enterprises and service providers. So I primarily work with companies to help them deploy cloud and SDN solutions for the purposes of improving processes within their business. All right, so why vCPE? I'm sure this is a topic that many of you have heard about. I'm sure most of you probably have initiatives, if you're a service provider, around vCPE. What's the benefit? Why are your business units interested in CPE? A couple of big reasons. The first and foremost is revenue. So how do we increase revenue growth for our per user base? The other is time to market. So how do we get new services out in front of customers faster? We do this through things like cloud technologies, improved automation, better configuration management. But it's also important for us to lower our capital and operating expenses. And so cloud is a good way of doing that. SDN in particular is a good way of doing that, moving away from purpose-built, high-end, expensive hardware devices, more towards a software-based model. Allows you to lower your costs pretty dramatically. And the final piece of vCPE is micro-segmentation. So we've got to have good ability to segment out our customers from each other. And that's for their security, that's for our security, and that's to make sure that the system runs as intended. So vCPE is really part of a broader trend, which is the evolution of service delivery. You know, we went from a traditional model where we were building on legacy hardware. Now we're moving towards cloud-based delivery, network on demand, faster time to market. We're moving towards application-delivered infrastructure. So moving away from a person at a keyboard making configuration changes or deploying new services, and into a model where the application and the code drives the deployment of new services and infrastructure. And again, this is to improve the speed of delivery. So how do we reduce the provisioning time from months to minutes? Moving from, again, having a person at a keyboard making changes to a model where the application is making changes in real time for you in response to customer demand. So how do we do this? We've got to have a model where we can move from the traditional big iron equipment, the forklift upgrade path, to a model where we're more agile, where we can deploy upgrades quickly, easily, safely. The answer for us is SDN and NFV. So moving away from those purpose-built hardware devices, moving towards virtual network functions, which are deployed in cloud architectures, and into a model that's fully automated. All right, so now we know why vCPE. What exactly is vCPE? How do we deploy it? vCPE is primarily three key functions. That's service insertion and chaining, virtual network functions, and NFV. And it's also the segmentation and the distribution of the control and data planes. So we want to have a strict separation between control and data plane functions, and we want to distribute those functions so that we can scale with our customer base. Etsy's come up with a virtual CPE model. From a very high level, we're talking about running our Layer 3 and to Layer 7 services, moving it from the customer premise into the cloud, and then delivering those services on to the customer from our facilities. Part and parcel to this, of course, is micro-segmentation. We can't deliver any service that's going to allow cross-talk or cross-communication between tenants, between end customers. The Etsy model doesn't specifically call this out, but micro-segmentation, I think everyone would agree, is a pretty hard requirement for any successful vCPE deployment. The second component is service insertion and automation and architecture chaining. So service insertion allows us to take third-party network functions, and this could be something that you purchase. It could be a checkpoint, or it could be something from Cisco, but it could also be, in many cases, a virtual network function which we've developed, and we want to insert into the packet flow. So service insertion and chaining allows us to take this third-party network function that's delivered in software and deploy it into the flow of packets. It could also be a hardware device, so it's pretty extensible. This, again, is to accelerate the delivery and creation of service. So we don't want to be in a position where a person has to go and make a manual physical change. Being able to insert it sort of dynamically into the flow allows you to deploy your services more quickly and efficiently. So the next part is the SDN and NFV model. And this is, again, the segmentation and the separation of the control in the data plane. And that's important for two reasons. When there's a problem in your environment today, you can be assured that network functionality will continue to process. In the software world, we're very concerned that the control plane could cause a failure of the data plane, which would be completely unacceptable for your users. And so separating out the control plane from the data plane allows us to not just scale independently, but also isolate our fault domains. So having a separate control plane that can fail, which wouldn't be ideal, but by the same token will not impact the flow of data in the environment, is very important. It gives us some ability to be more flexible as well. So it's easier to provision and troubleshoot. Having the control plane separate from the data plane, if you need to restart the control plane for any reason, you can be assured that this isn't going to impact the data plane. The data plane, though, has to be robust, and it can't be an application which fails in a way which would impact the flow of traffic. And so it's got to continue to enable the local forwarding of services. Again, it's got to be easy to provision and patch and upgrade. We can't have a situation where we're taking down our broad swaths of our customers as we're going through upgrades. One of the key benefits of vCPE is being able to do large-scale upgrades efficiently, easily, and in a way which is transparent to our end users. All the while, of course, this is running on generic hardware, moving away from that high-end enterprise type equipment. So how do we do this? PLUMgrid, the company that I work for, has created a project called Visor. This was based off of some code which we developed and we've open sourced, and we've built a community around. The community is part of the, or is hosted by the Linux Foundation. And it's not just a PLUMgrid project any longer. Facebook, Netflix, Huawei, Cisco are all contributors. But this is the model where we separate out the control and the data planes. Visor, the component, is the data plane. It lives inside the Linux kernel. Anybody in this room that's running Linux on a device can mod probe in Visor right now if you're running a modern kernel, completely open source and free to use. And it gives you the capability to virtualize your I/O, not just from a network perspective, but also from a storage perspective. So Netflix, for example, uses Visor to profile and troubleshoot storage performance problems. We use it as part of a networking suite. We use the programmable data plane as part of a networking suite to facilitate network communications inside of OpenStack clouds. So it's very extensible. Anywhere input-output is used on the Linux kernel, Visor can be inserted into the path. All right. And as I mentioned, we've got a pretty broad array of industry as well as enterprise partners who are working on this project and contributing to this project, using this project to facilitate and enable their business. So from a high level, the Visor is about two things, flexibility and performance. Flexibility, it's programmable, extensible data plane. It's dynamic I/O modules, so we can load new plugins into the Visor stack while it's running. It's a portable across any platform, so it runs anywhere that the Linux kernel runs, which is important. So it's not just a small set of equipment. The performance, being in the kernel, it's high performance. I know there's a lot of debate about which is faster, kernel mode or user space. The answer is, of course, code runs at the same speed in both kernel mode and user space. The benefit, however, of having your network functions delivered in the kernel is we avoid the context switch. So for applications which are deployed in user space, even though they run just as fast as the code that's in the kernel, there's a performance penalty when they have to issue a context switch to get to kernel mode. So that's why we believe, and why we'll show you some slides in a little bit, that the performance is both more consistent and higher performing. This also allows us to distribute the data plane. So each one of your compute nodes now is sending traffic directly onto the network. Traditional OpenStack clouds require a network node as a sort of centralized bottleneck and point of failure. And it allows for scale out forwarding. So as you add more compute infrastructure, you're adding more network throughput, network performance. There's a linear scalability pattern there. All right. From a high level, what's in the IO-Visor project? I mentioned already that we've got an IO-Visor kernel module, so that's dynamically loaded. But we also leverage some user space tools for controlling IO-Visor completely outside of the data plane. Also have some troubleshooting and traceability tools. But IO-Visor also has an extensible plugin architecture. So we can plug in tools for not just networking, but security. Also storage, I mentioned earlier, advanced tracing functionality. If you think about some of the functionality it's enabled in tools like dtrace and system tap, those are all available inside of IO-Visor. And so it gives you a really rich set of features to deploy, not just for network function virtualization, but also for troubleshooting and performance monitoring of your environment. As I mentioned, I wanted to show a slide on performance. A couple things will pop out here. First, what we're showing is network throughput between pairs of VMs inside of an OpenStack environment. And we're comparing against the vanilla Neutron implementation. Neutron is a combination of Linux network namespaces, OVS, and IP tables within those network namespaces. Of course, we always like to see that the IO-Visor outperforms the OVS solution. But most importantly, I think for us, many of us are service providers, the performance is consistent. With the user mode implementation of OVS, what we see is more throughput is pushed to the system, we get inconsistent results. And this is okay for workloads like websites, right? It doesn't really matter if a website loads in 25 milliseconds or 100 milliseconds. Your user probably won't notice. But for telecom applications, this is incredibly important. You've got to have consistent performance every time. So a couple of IO-Visor use cases. We've got some slides to discuss each one of these. As I mentioned before, it's not just about network function virtualization, but also about the tracing capabilities that are built into IO-Visor and eBPF, the programming framework inside of IO-Visor. It allows us to do things like security monitoring and enforcement. Because we live inside the kernel and because we're the interface between the system and the I/O layer, it gives us a lot of really valuable information and control over the flow of I/O through the system. This, of course, can also be used for storage monitoring, performance improvement, and as I mentioned, Netflix is a big proponent and consumer of this technology. All right, so why don't we take you through a simple use case example from a networking perspective. IO-Visor, particularly within PLUMgrid, is used to build a fully distributed virtual network across your compute nodes. All the data plane components are inserted dynamically into the kernel, so as I mentioned before, you don't have to take an outage to insert this kernel module. You can insert the kernel module and begin using it. There's no physical or virtual appliance necessary. This is a completely software-based solution. Other SDN solutions require top-of-rack gateways or end-of-row gateways. IO-Visor does not require that. We put traffic directly on the wire, and we create a VXLAN overlay. We use that to virtualize the network functions, so NAT, DHCP, DNS. And that gives us some capabilities to do some advanced tracing. So what you'll see on the right is a tunnel graph of endpoints within an IO-Visor system, so showing the throughput between virtual machines within the data plane, which is incredibly important when we're talking about networking at scale. Having some detailed information about how your applications and your systems are performing, and knowing who the main consumers of your application are. These slides will be available as part of the presentation. We've got links in here. If you want to try out the examples, you can download them and run them directly on your setup, so you can see how this works for yourself. And then the last real example here is the storage monitoring. Again, this is a slide that's based off some work that Netflix is doing, but they're using it to profile and create histograms for I/O workloads inside of their environment from a VFS perspective. So taking performance of their I/O devices and putting that in front of a network operations center. All right, I think I'm about out of time, so why don't I put up the thank you slide and open up for questions. Thank you very much.
Evgeny Zobnitsov, Factor Group. I just wanted to ask, do you really mean that any Linux kernel running on any device can be manageable and trace it from the IO Visor project itself?
We do. Anywhere that the Linux kernel runs 3.16 and higher, recompile, of course, for your particular architecture, but yes.
Thank you.
Алексей Семенека, Curator Labs. У меня не вопрос, у меня замечание. Я хочу...
The question, it's a comment. I'd like to thank the speaker. Effectively, the post-Soviet segment has a great deal of specifics from the viewpoint of the broadband. So the broadband that in Russia and Ukraine, well, Russia, Kazakhstan, and the CPE are owned by the users, and the CPE in the West is owned by the operator. And so that changes the situation when with IPv6 deployment. That's the difference. And this is the cheapest way, the simplest way to change to translate IPv6 into the broadband. This is the best way to do it, and this is the best way to migrate to the system because of different ownership. Да, совершенно правильно.
Or component of IO Visor. We have telecom providers leveraging it for their IPv6 solutions as well.
It was just noticed, and I will describe you separately.
Okay. Thank you.
Thank you.
Great. Other questions?
Thank you again. The next